Well, then, we are live with the unbelievable episode 60 of Space Rocks Uplink. What a delight it is to be joined by people from, I'm guessing, all around the world. And, well, we're joined now by Mark McCaughrean. And, well, I got to say, Mark, you kind of fit into that category now. You've been traveling just a little bit. How nice it is to have you back.
Indeed. Let me just sort my audio out here. Seems I've been traveling and I've got things connected the wrong way. That should be better. Yes, indeed. I've actually been on a plane for the first time in nearly 2 years. Quite remarkable. Yeah, the end of last week, I was lucky enough to fly to this place, which is behind me here. Well, to the airport, not so far away. This is the place we call Jupiter. It's the Jupiter control room at our French Guiana launch site at Kourou. So where we launch our rockets from. European Space Agency in collaboration with the French Space Agency CNES and Ariane Space, of course, who provide the rockets. And this is the control room. In fact, if the way it looks in this picture is the people launching the rockets are looking towards where I'm standing. So if I was to turn around, they would be seeing a big screen above my head, and that's where they see the rocket. And from this room, Jupiter to the Ariane 5 launch site itself is 12 kilometers, so it's quite some way away. But indeed, yes, quite the weird experience to get on an airplane and sit on it in a metal tube for 8.5 hours.
Well, on that, so why is it so far away? I mean, why not just, build it in Holland, right? I mean, surely you could just launch things from Aztec, just go up the road and do it from there.
Absolutely, it's flat enough and there's plenty of landscape. I mean, the two fundamental reasons are that it's close to the equator. It's just 5 degrees north of the equator, and it also has an ocean on the eastern edge. So it's sitting on the east coast of South America, French Guiana. And that means that when you launch the rockets, the Earth is rotating in that direction. So you actually get 1,600 kilometers an hour extra shove in the direction you want to go because the Earth is rotating you already. So that makes the rockets more efficient. And because there's an ocean right there, if something goes wrong or when you drop the solid rocket boosters and so on, they go into the ocean and they don't go onto land. So that's why typically you see that same thing in Florida for KSC, Kennedy Space Center. That's on the east coast of the United States. They have the ocean right next to them. And here in the Netherlands, it's the other way around. We're on the west coast of Europe, so launching west from here is not effective.
Indeed. Well, I mean, it all makes a certain kind of sense. I didn't think it was accidental, but I guess it does kind of add to the I guess the journey that you've been on, And I've got to say, as an observer, the drama as well, because I mean, well, I mean, just all things going to current plans, presumably. A little later this year, it's the beginning of an extraordinary journey, and I guess that's what we're talking about today. We've discussed the James Webb Space Telescope already on this program. It tends to come up as well. You're personally involved, correct?
Yep.
And I suppose, I mean, on the scale of telescopes, on the scale of instruments, I mean, this does feel kind of like you could say, kind of a big deal.
Absolutely. I mean, you mentioned this at the beginning of the journey. It's the beginning of the next step. I've been involved for 23 years. Other people have started on this as early as 1989, so it's taken a huge amount of time to get to where we are. And why? Because it's incredibly complicated. This is a huge observatory, which we'll talk about in more detail later on. But broadly speaking, it's a main mirror is 6.5 meters across. A Sunshield the size of a tennis court, and in order to fit that into a rocket, it all has to be folded up origami style and then deployed in space. And we'll get into some of those details today. But it's an incredibly sophisticated, clever piece of technology. And not only has it got to unfold in space, it's got to get to ridiculously low temperatures, minus 233 degrees Celsius, in order to function the way that it's designed. So, yeah, very complicated machine. And I think perfectly reasonable to call it, kind of the next great step in astronomy. The Hubble Space Telescope, 31 years old. It's taken us kind of this long to get to this point. Ground-based telescopes, of course, have changed enormously. We're talking about huge telescopes on the ground in the next generation. But as far as space telescopes go, this is the one, and it's been long awaited.
Indeed, long awaited. And I guess we have two people that are uniquely suited to tell us all about what needs to happen over the next, gosh, can it be just 6 weeks time, something like that? I mean, my gosh, what an exciting moment. So tell us a little bit about Kate and Sarah, and of course, if people have engaged with Space Rocks before, they'll know a little bit about Kate Underhill.
Yeah, so Kate is somebody you've had on Uplink before, talking about rocket propulsion, and that's her background. She's a rocket engineer, a true rocket scientist, if you like. Unlike the rest of us who just use the rocket to get to space and then start doing science, she understands how the rockets work. And she was on stage with us in London that would have been 2019 at our second Space Rocks big event there in London, talking again about trying to get kids to understand the rocket equation, which is a bit of a challenge, but it's one of the most basic things in rocket engineering. So it's great to have Kate back, and she'll be talking us through how the Ariane 5 rocket, the European rocket, will be putting James Webb Space Telescope into space. And then Sarah Kendrew is a colleague of mine in the science directorate, and she's an astronomer, and she has this title, Instrument and Calibration Scientist. So she's actually based at the Space Telescope Science Institute in Baltimore, where we have had a contingent for many years in our collaboration with NASA on the Hubble Space Telescope, and we do again. We have roughly 15 people there for James Webb Space Telescope. And so Sarah will be in the front line as the instruments get turned on after launch of Webb. And she understands better than anybody how these instruments work in terms of the interplay between the science community making a proposal, saying, I want to observe such and such an object at such and such a wavelength in such and such a manner. How do you then turn that into an actual observation and, wheels turning and detectors taking pictures on the telescope, and then bring the data back down to Earth from 1.5 million kilometers away? So, and her speciality on James Webb is actually one of the instruments called MIRI, the mid-infrared instrument. So I'm really looking forward to hearing from Sarah about how MIRI actually gets turned on. It's not going to start taking images on the first day. It's a long process before that's possible. And it's down to people like Sarah that will be able to do that.
Indeed. Well, it's going to be a fascinating conversation. Sarah's going to be joining us just a little bit later in the hour. But first up, let's bring in Kate Underhill, or welcome her back, we should say, to the fray of Space Rocks. I guess you might not be able to see it. Rocket Kate, how are you doing?
Hi, I'm good. Thank you. Lovely to see you again.
Likewise.
Lovely to see you again. Sorry, Mark, go ahead.
Yeah, no. I mean, and I know it's not exactly private, but I should point out that every time you're on Space Rocks, it's something about Space Rocks that makes you make babies. I don't know what that is exactly. But, so it was amazing when you were pregnant with your first child, more than a couple of years ago now.
Just over 2. You just turned 2.
Yeah, September 2000, and there you were explaining the rocket equation, and amazing. So I suppose you've been busy during lockdown is the obvious thing to say, but
it's a tradition I like. And when I'm pregnant, I come on Space Rocks. We should keep it up. I think I'm going to stop. Let's after this one.
No, we've got plans already for another seven episodes.
Well, congratulations, Kate, and welcome back. And it's going to be a few minutes before Sarah joins us for the program, so it might actually be worthwhile to flip to something even more topical than JWST, right? Because of course, so many people in the world are watching the proceedings at COP26 and so on. And it's talk about emissions. It's talk about everything. What can we do as a species and all that? And every now and then, in the context of space travel and exploration, the subject of rockets does come up. I mean, how does engineering and propulsion engineering fit into this new way of thinking about, I guess, how we can be better inhabitants of Earth?
Yeah, exactly. It's really this idea of kind of being ecological and being green is really becoming part of everything we do, and especially as ESA, the European Space Agency, we're an intergovernmental agency. We're the ones that really have to kind of take this seriously and push this forward and say this is something we need to take into account in all of our projects, and it's going to be more and more important in the future. And it's very easy for us to say, Ariane 5, it has hydrogen, oxygen. When we burn it, the emission is water. So the rocket itself is relatively clean. But then we have the whole life cycle process. How do we make the rocket? How do we make the hydrogen that we're then burning in the rocket? How do we dispose of the parts afterwards? And this is something that we are looking into for the future. So Ariane 5, we have all the on the launch base, which we will talk about later. We have all the installations that make hydrogen today, that make the solid fuel for the solid boosters. And we're looking into kind of post 2030, what launches do we want? What launches do we need for Europe? And also how green can those launches be in terms of their complete life cycle? And one of the examples is we're also thinking now about making a mixture of methane with oxygen as a propellant, where we think we can make methane with bioproducts. So have, again, the circular economy, take agricultural offloads, agricultural leftover waste, and bring that into the launch base and start making methane from it. So really kind of also integrating ourselves better into local economy and having a circular economy and having launches that are really kind of green throughout the entire life cycle and not just the flight.
So when I was talking, I was lucky enough to be at Kourou last weekend and talking to one of the Ariane space engineers about where we get our hydrogen. He told me that it's effectively methanol is bought by Air Liquide, the French company that has the factory, the production plant there in Kourou. But it wasn't quite clear where that methanol was coming from, whether it was coming from, effectively methane out of gas wells, or whether it was actually already coming from bioethanol and methanol. I'm not sure if do you know the answer to that? Because it wasn't obvious. I mean, it's kind of, we buy the hydrogen, but we don't know where the methanol comes from.
I'm not sure entirely. I don't think it's quite bio enough yet for us. And there's also the energy production. It's very energy intensive. And at the moment we use a lot of the energy produced in French Guiana. I think 1/3 is used by the launch base. And then quite often we take ourselves off grid, and then we have our own fuel generators that are just very not green. And we're looking into this whole rehabilitation of the launch base now. Lots of solar panels, lots of green energy being produced there. So every aspect of the production can become greener.
Because just to dig in on that point, the alternative to this blue hydrogen, as it's called, is green hydrogen, where it might be made by taking water and splitting it with electricity directly. But then that's a lot of energy which French Guiana doesn't have, right? I mean, as you say, it's a small country, relatively small population, and not that wealthy. So just stealing all their energy doesn't kind of make sense at the moment.
No, exactly. Like I say, we actually the French, the EDF uses the CSG as a controller of the network, and so when there's a peak on the network, they ask the CSG to take themselves off the network because there's such a huge drain on it. And then they said we have our own fuel supply to do that, which is very unecological. But there is a lot of sunshine in French Guiana, so there are ways of producing electricity in a greener way, and that's something that we are now investing in within ESA and within our launch base.
And as would be no mystery to anybody who's ever been to the tropics, there's also an awful lot of rain in French Guiana, but it comes and goes, right? It gets hot and sticky because of the rain. As soon as the sun comes out, woof. It was an interesting couple of days at 30 degrees centigrade and 100% humidity, and then back to Europe again.
I remember the first time I took the plane to French Guiana, and you get off the plane, and just when you walk off the plane into the airport, and you just get this wave of humidity, and it's you've gone somewhere different.
Indeed. And I dare say that you got there a lot more quickly than the James Webb Space Telescope, of course. I mean, a lot of people were watching that sort of, make its way down there. It crept down there. And I mean, just really quickly, what's involved with transporting an instrument to that? Because I guess it's not just about bubble wrap, is it? I mean, you best tech and so on. I mean, it must be an extraordinary feat of engineering in itself just to get it there safely before it's put into the launcher.
Oh, in fact, very handily, we had a special boat that was available already. We have 2 boats that have been produced for transporting Ariane 5. So Ariane 5, the European launcher, is actually produced in Europe, in various locations in Europe, and then shipped to French Guiana across the Atlantic. And there's actually 2 boats, the MN Toucan, which is Toucan, and MN Colibri, which is a hummingbird, that have been built to be large enough to carry one Ariane 5, that are able to go across the Atlantic, and are also able to go up the Kourou River, which is very shallow. So they're very, very shallow boats. And in fact, one of these boats was used to transport James Webb from the US, where it was built, from California, down the US through the Suez Canal and into
Panama
French
Canal.
Guiana.
Panama Canal.
Panama Canal, excuse me. Yeah, the right canal.
It didn't have that long a journey, but
yeah. And so the boat has been built to transport very expensive launcher parts. So it's very well attached. We have all sorts of sensors, humidity sensors, shock sensors, everything, camera, everything to make sure that it is having a nice journey and it's not getting wet on the way.
And of course, Webb has this enormous container called O-Stars, which is pressurized and temperature controlled and humidity controlled and so on. So it was inside box upon box upon box. If you look at the video online, this unboxing video when it came out is, yes, well, if you like unboxing videos of expensive bits of electronic equipment, go and watch that one because it doesn't get any better than that.
Indeed.
Yeah, because just say the electronics don't like the humidity in French Guiana. So exactly, we are used to being able to control everything and keep everything dry by lots of boxes and lots of flushing of dry gases.
Yeah. Well, speaking of instruments, we're going to be joined by Sarah, who is just coming aboard. And Sarah, how are you doing? Are you receiving?
Receiving you fine and clear. Thank you. Hello, everyone.
Hi.
It's a pleasure.
So we should say that it wasn't just that you were late, but you're actually doing some work because you're based in the US and it's still work hours, right? So.
Correct.
Yeah.
Indeed. Well, Sarah, welcome aboard, and thank you so much for joining on behalf of everyone at Space Rocks. And we were actually just talking about the James Webb Space Telescope, wouldn't you know, and just how delicate those instruments are that have made their way down to French Guiana, and so on. And I guess as Mark kind of alluded to before, I mean, Mark, correct me if I'm wrong, you said you were involved with James Webb Space Telescope for the last 23 years. Where did your journey begin? Because for many people, it's the first time they're hearing about this amazing instrument, but it's been underway for some time. So how did you first become involved? Where did your own story begin?
Yes, thanks. Good question. I'm not quite as much of a veteran on Webb yet as Mark is, but it's been a long time. Yeah, it's been coming up to 4 years soon. I joined the project in 2008. So I'm an astronomer by training, but already for my PhD, I really worked on the technical side of astronomy. So I did a PhD in a field called adaptive optics, which is a kind of a ground-based observatory technology. So I was always really interested in like the technical, the engineering aspect of astronomy. And it was in my first postdoc, I was working in the Netherlands on a ground-based instrument, in fact, but I was given the opportunity to join the team for MIRI. So it was at a time when the hardware for MIRI was really starting to take shape. And all the optics for MIRI were mostly all developed and constructed in Europe by a large consortium of European countries and institutes and universities. And so we were really planning ahead to, how the instrument was going to be assembled and tested, and kind of starting to put together that European team for MIRI. And I moved around a lot in Europe. I had different postdoctoral appointments and worked on other projects along the way as well, but have always kind of stayed with the MIRI team. And then about 5.5, almost 6 years ago now, ESA hired me was brought into the fold, into the family, and moved to Baltimore to really be kind of at the heart of the mission operations in the run up to launch, and then after launch as well.
So just for everybody watching, let's go briefly through the telescope as it is as a machine, right? So there's a front end. There's a big mirror that actually made out of 18 segments that collects light, focuses it into the back. And so what's in that back box, the thing we call ISIM, the Integrated Science Instrument Module? Because there's lots of stuff going on there. In fact, that's where we detect all the photons to do the science.
That's right, yes. So we have this kind of instrument package that sits on the back of the mirror, all held together by this module called ISIM, the Integrated Science Instrument Module that Mark mentioned. And so that's really, ISIM is kind of like the hardware that all the instruments are bolted onto. And we have 4 science instruments on Webb. We have 3 that observe in near-infrared light, and that's Nurcam, Nurspec, NIRIS, all starting with NIR, signaling that they're near-infrared. And then the fourth instrument is MIRI, which is the one I work on, which observes all wavelengths kind of in the mid-infrared, so from about 5 to 28 or so microns. And so we can use an instrument individually. We can partner some of them up together. They each have their own kind of patch of the focal plane of the telescope that they observe. Each of these instruments has multiple different observing modes on board. So they have different types of cameras. They can do spectroscopy and imaging, different, all kinds of different types with lots of different filters and gratings and things like that. So really each of the instruments is incredibly powerful in their own right, and really optimized to address a wide range of different kinds of science topics and observe lots of different types of targets. And together they're an incredibly powerful instrument suite together that's going to be able to really really kind of use the telescope to the maximum extent.
So if I switch back to you now, Kate, I mean, one of the biggest challenges of Webb in many ways is the fact that, you rocket guys couldn't build us a big enough rocket. I'm sorry to put it that way, but, I mean...
5.4 meter diameter, come on.
Well, it is big, but of course it's not big enough to hold the whole telescope unfolded. And so that's, as I mentioned in the introduction, there's this sort of astonishing feat of sort of... It's almost like taking a butterfly, folding it back into a pupa, and then expecting it to come out the second time the way that it went in. So you talk us through a little bit about that top end of the rocket. I mean, we're familiar that there's propulsion at the bottom end, but that top end is pretty sophisticated on this Ariane 5, specifically for James Webb, right?
Yeah. So in fact, with a little bit of history, the first Ariane 5 launch mission I was on was actually Herschel Planck. And Herschel was at the time the largest mirror to be launched into space. And now it's being taken over by James Webb. And like you say, James Webb is so big that we can't fit it in one piece under the fairing. So even though the fairing is 5.4 meter diameter, which is one of the largest fairings available on launches in the world, once it was decided that James Webb was going to launch on Ariane 5 as part of the European contribution to the mission, the engineers had to work out how to origami fold the mirror and the telescope and all the instruments and all the solar protection under the fairing. So we have a very specific fairing volume, and in fact you have the fairing, which is the protective cover on top of the rocket, which actually only lasts 2 or 3 minutes into the launch, because after 3 minutes we're already enough out the atmosphere that we can drop it. But we need this protection at the beginning, and we have a very defined volume inside the fairing that a satellite is allowed to take up, and this gives us some margin because there's vibration obviously during launch. And I just understood with James Webb, apparently we are 1 centimeter away from the limit of the margin. So there really is no margin whatsoever. And when I worked on the launch operations, I did the fairing integration for ATV, the ATV-2 mission, and there we had 20 centimeter margin between ATV and the fairing. So that's not a lot, but it was enough. And I think there's going to be even less for James Webb. So the person doing the fairing integration is going to have to get their precision on just right to be able to get in.
And then, sorry, just before I hand back to Alex, I mean, one of the key things is that it's not just a standard fairing. There are 2 modifications, as it were. One, I mean, if we come to Sarah on this, I mean, one is that that fairing has to be fantastically clean compared to other fairings for other satellites, because Webb is a completely wide open telescope. I mean, it's folded up, but the optics are not under covers at all. They're all sitting out there. So maybe, that's sort of the first question. Why does it have to be clean? And then we have this issue with the Sunshield and this depressurization issue. So maybe we can talk about that secondly with Kate. But start us on, why is it important that JWST be clean? Beyond, just the sort of, it should be clean. It's more, it's for science, right?
Yeah. So, I mean, there's lots of different aspects to that, I think. First of all, any kind of dust can settle on optical components and can cause, the reflectivity of the mirrors or the throughput of, of things to decrease. So we really want to, and things like a speck of dust, if it's like depending on where it is in the optical path, it doesn't just look like a little bit of dust. It can actually cause all kinds of like weird patterns as well. So just like a bit of dust can actually have quite a big impact on what the data look like. Also things like molecules you know, certain molecules, they can kind of like, because the whole observatory will go through quite a lot of like temperature variations throughout the launch sequence, and then once it's in space. And so you don't want things like freezing onto the optics as well, which again can actually cause like chemical signatures in the data that can confuse what you're actually looking at. So there's lots of different aspects to that actually, but it is very important to keep the observatory as clean as possible. And it's incredibly impressive to see what goes into that when the observatory is on the ground. You know, this is why in so many of the pictures everyone's in bunny suits and every piece of their body is covered up.
And then this other modification to the Ariane 5. I mean, of course, they try to keep the fairings clean, but I know that a huge amount of effort's been put into keeping that fairing clean when it was made in Rouag in Switzerland and transported to French Guiana. But this other thing is this modification with these slats, these vents in the fairing to allow the fairing to depressurize. All the air inside the fairing has to get out. And ideally before the fairing itself separates, because that would create a big pulse of depressurization. I mean, I'm not deliberately putting you on the spot, but you know that's kind of important for James Webb, right, Kate?
Yes. Like I say, I'm an expert on the launcher, so I know exactly what we've done. But this does happen to Ariane 5. We have a standard Ariane 5, but we do have modifications for certain customers, and especially when it comes to satellites like this. And I'd just go back to cleanliness. Obviously, it's always clean. All satellites have a certain cleanliness, and we have clean rooms in general. But this is effectively a whole other level of cleanliness protocols that we put in place in the clean rooms once we're on the launcher. And take example of Herschel, that also was a mirror that had to be very clean, and they had a protection that was taken off. Literally, someone pulled the blanket away at the last minute. ATV, we had to completely dress up again to make sure there was no bacteria going up onto the space station. So we have been able to do things like this before, but I think this for James Webb, it really is another level to keep sure we get everything perfectly clean. And then for the venting holes, effectively, it was a requirement from the satellite that it was very sensitive to depressurization. And as I just said, we go from 1 bar ground level up to 0 bar within 3 minutes, and that pressure has to go somewhere. Obviously, on the ground, we don't let the external air in because it's hot, humid air, which is going to be very bad for the satellite. So we have a lot of flushing. We're making sure air is going out, but we don't have big holes on the fairing. So we've had to design specific holes that are enabling us to release that cold, dry air that's 1 bar in the fairing as we go up in the flight as smoothly as possible. So like you say, that by the time we get to the fairing separation, we're at 0 bar, we're at a vacuum like the outside, and there's no shock whatsoever on the satellite.
Yeah, it's this business of the Sunshield, right? The fact the Sunshield is a big floppy structure, although it's held down fairly well. That if it might, ripple and pulse and maybe even rip if the pressure differential at that last step is not low. We
need to give it as smooth a ride as possible.
Yeah.
I didn't know about this, and I now have another thing to worry about.
Well, that's an item number 4,732. Right?
Thanks, Kate. Yes.
Yeah, I mean, on previous tests of the Ariane 5, that depressurization was measured, and it wasn't found to be enough for that last phase. That when the fairing separates, there's just that final pulse, and that was in excess of the amount allowed for the Sunshield. So the Arianespace engineers built in, or the Rouag fairing guys built in these extra flaps all the way as a ring all the way around the fairing, but which, as you say, only open when we're in halfway to space, so to speak. So there's no
there's near enough vacuum. Yeah, and the last Ariane flight has been really useful for us. We really confirmed the last Ariane flight, which was in July, August, has an absolutely perfect flight that showed off that the last kind of remaining elements that we needed to qualify, the changes we need to qualify James Webb, have all been checked out and confirmed. So we're now very happy to go ahead with the James Webb launch.
Indeed. Well, I mean, this is the thing, though, isn't it? We talked about, kind of jokingly, the journey of James Webb to the launch pad, but I guess it's really just that final stage of its journey, which is kind of extraordinary, and one imagines, well, slightly nerve-wracking to an observer. I think we'll all be watching just with great interest. But I guess this is the thing. I mean, how does an instrument that sensitive withstand the forces that are at play when it's actually leaving the Earth's atmosphere? I mean, I guess by any standard, perhaps the most traumatizing part of its journey is just that final stage. I mean, how do you build and test, and how do you know that it's going to kind of get into outer space safely?
If I can just start off answering that one, is you read the Ariane 5 user manual, which is actually available online.
Always read the manual, basically in the glove box, just hit it, just sort of detaches. Yeah, that's what I thought.
And it defines exactly. It's a really interesting document, if you like those kind of things, but exactly defines the shock level, the complete environment that a satellite has to be able to survive. It has to demonstrate that it can survive before we accept to launch it, in fact, as a payload. And there are certain elements that are linked to the satellite itself. So effectively, the launch, once you're in space, it's very smooth. There are no shocks. So really, is the launch that is the defining requirement in terms of kind of shock and vibration environment for the satellite. So this is all described in the launch manual, and it gives you margins. So you need to demonstrate this much shock and vibration on your part, and then once you've done that, then we confirm that the satellite will survive the launch. But there are also other elements where we say you need to make sure your satellite doesn't do this or this, because that will interfere with our launcher. So there are things like electromagnetic interference. So we also have asked tests on electromagnetic tests on the satellite so that it doesn't confuse the launcher, it isn't on, and it isn't giving commands to the launcher while we're launching. And so all of these are defined in the user manual, and then it's up to the satellite manufacturer, once they make their parts, to make the parts and test them and confirm that they are compliant with the requirements.
So talk us through that first stage then. So we're sitting on the launch pad. There's somebody in this control room behind me here counting down in French, which will be interesting for all our American viewers. And of course, the rocket doesn't take off at zero, unlike everybody's used to in the films. That's not how it works with Ariane. So talk us through that stage. What is the controller here, the DDO, and what happens at the beginning? How does an Ariane 5 work?
It's complex, obviously. No, so obviously we've done the whole integration operations. I know kind of, we've assembled the satellite, we've got it ready, we've fueled the satellite, we've put it under the fairing, we've put it all on top. We put the satellite and then the fairing on top of the launcher, and we've checked and double-checked and triple-checked the launcher, and then we have an agreement that we go out into the launch pad. All of this is in the assembly buildings, and then we have a special meeting. We say, yep, the launch campaign has gone well, we're happy, everything's ready, and then we roll out the launcher onto the launch pad. And then we have our final countdown operations, which is about 12 hours in total. We do lots of manual operations. It's pressurization, it's filling the tanks, going to the gas station, filling your tanks up, charging the batteries. And then we get up to what we call the synchronized sequence, which is the last 7 minutes, which is in fact completely autonomous. So in the last 7 minutes of the countdown, there is a man counting in French, but he has no impact whatsoever on the launcher. The launcher is looking after itself. 7 minutes, we're hands off, we are watching, we're getting all the data from the launcher, but it is going through its final maneuvers, its final pressurization, final fueling, and it's checking itself out, into making sure it's ready to go. And then we have H0, which, as you say, is not liftoff for Ariane 5, because what we do then is we ignite the main engine, which is a Vulcan 2 engine, which is burning a hydrogen and oxygen. And in fact, we burn that for 7 seconds to make sure that it is working correctly. So this is a kind of a last final hot fire test, check, okay, our main engine is all right. And that point at H0 plus 7 seconds, where then we ignite the solid boosters, which are on the side. And those are the ones that give us this real oomph, give us the thrust to get off the ground. And that's when we have liftoff, décollage. So at that point, Ariane 5 takes off and is on its way to space.
So just before we leave that, I mean, there was this beautiful moment last week. I mean, the thing is that when you start the Vulcan, you are holding the ERPs, the solid rocket boosters, down. The rocket cannot move at that point, so there is an explosive release. But
no, the Ariane 5 just sitting on its launch pad.
Yeah, because that was the thing. That was the thing that was surprising, is that there's no way of it's not held on to that launch table when it's driven out. It's just standing there. It could fall over with a gust of wind.
This is something when you're doing a transfer you think about a lot, because it is just sitting on its solid boosters. There is nothing holding the rocket down.
Yeah, because we're kind of used to watching Apollo, for example, where Apollo had these huge bolts which lifted away so that the rocket could go, and that just doesn't happen here. Nothing's holding it there. So the Vulcan is obviously not enough. Yeah. It's only a fraction of the total power at this point. Do you remember the fraction? How much the Vulcan is providing at this point? I mean,
Not exactly.
It's like 10, a few
Yeah,
percent.
10,
but
20%, something like that.
yeah.
It's around that area. So it's really the boosters that get us off the ground. But they are 200, so just 240 tons of propellant each, and they are burnt out within 2 minutes. So we burn 240 tons of propellant in 2 minutes. And then by that time, the rocket itself is going fast enough and it's light enough that the Vulcan main engine then has enough thrust to keep it going for the rest of the main flight, which is 9 minutes in total.
And I think the one thing which is always fascinating is how explosive those solid rockets are, right? When you hear them go, there's not kind of unlike the Vulcan, which kind of goes whoosh as it starts up, the ERPs blow up, basically. I mean, it's this crazy big booming sound.
It's a booming sound and it's a huge flash of light. And I keep saying every time anybody sees a launch, you just have this wonderful discussion afterwards, like, was it the noise or was it the light that's more impressive? Because it is just this, really kind of explosive energy, noise and light as they ignite and as they lift off the ground.
Yeah, and Ariane 5 is quite quick as well. It's gone quite quickly, right?
Because again, we've got these solid boosters. It's quite constraining for the payloads because it is quite a shock. We get off the ground very, very fast, and the boosters push us very, very fast up into space.
So let's talk through those 9 minutes, because you get rid of the solid rocket boosters, and then the Vulcan is powering. Get rid of the fairing fairly early on, right? Because it's
3 minutes.
It's just extra weight, and you're above enough of the atmosphere at that point that it's not going to be any aerodynamic.
With launches, as soon as we can get rid of the weight, we get rid of the weight. And again, that's part of the launcher equation I was trying to teach children, is that staging. So what we call staging is, it's not that easy to get into space. It is rocket science, and part of the way we do it is by separating it in chunks. And as soon as we've used the stage, as soon as it's given it all its energy to the rocket, then we drop it because it's just dead weight for us.
And then there's this phase where we actually get rid of the whole core stage of the Ariane 5, but there's still an engine, right? Because we're not where we need to be yet. So talk us through that cryogenic upper stage.
Not yet. So the EPC gets us to, I think, above Africa in 9 minutes, from South America to Africa in 9 minutes. But that isn't very far, isn't far enough, isn't fast enough yet. And then we have the upper stage, which is called the EAC, which is another cryogenic upper stage. So again, hydrogen, oxygen, powered by the HM7B engine coming from Ariane 4 for the history buffs. And this is upper stage is the one that's going to really get us to the speed and the place we need to be to release the satellite. Now, the upper stage will not take James Webb to its final location, which is the L2 point gravitational kind of well between the Earth and the Sun, but it will take it on a transfer, what we call an L2 transfer orbit. So it's going to point it in the right direction and give it the right speed to get, and then James Webb will have to manage by itself. So the upper stage will burn. So the mission in overall complete mission is 27 minutes. So we have 9 minute flight of main stage. I think then there's a bit of a ballistic stage. We have separation of the stages. We have we lose a little bit of altitude in order to gain speed on the upper stage with the satellite, and then we ignite the upper stage, and then that burns for 15-16 minutes to get us. And then it's doing these calculations. It's doing a little bit of a orbital to really get the satellite in the right direction. And again, I'll go back to the last Ariane 5 launch. The precision of injection on the last Ariane 5 launch was really breathtaking. It's kilometers. For orbital distances of 10,000 kilometers, it was a plus or minus 4 or 5 kilometers, really getting you exactly where the satellite needs to go, which means the satellite itself has to do less work, which means the satellite has to use less propellant, and then it has a longer lifetime because it has more propellant to do its mission keeping operations. So after 27 minutes, the upper stage will release James Webb in the right direction with the right speed, and then the upper stage itself, and this is another modification we've done, has additional power, additional battery to put itself off, take itself away, put itself in a safe orbit, so it's not going to interfere with James Webb or any other satellites.
And before we leave that part, I mean, the other remarkable thing to me is that, in fact, there's this real interplay here, because you don't want that upper stage to overperform, because you don't want to go beyond the L2 point. So you actually leave it kind of a little bit short of getting to L2, which of course is not just a place, it's the thing we orbit around 1.5 million kilometers away. But that we do need to use the propellant on board of James Webb to actually get us to that right place. On the other hand, that propellant is it's the lifetime limiter essentially for the science. Yeah. And so we want to use as little of that as possible in this phase, because the operations for the 10 or maybe more years. So yeah, I mean, it's this utterly, beautiful balancing act. Let's get it exactly right, but not, don't overdo it. So
as far as
I
you
like
can.
to say, don't be an Australian and overperform just to show off, right? I mean, let's get us to just short of what we need to, so that we can use the thrusters.
And this is where, so Ariane 5, we have the advantage. It's a well-known launch. We've launched it for a number of years now. We've had 100, 150, more than that launches. We know the upper stage now, and also the engines are tested beforehand. So everything is calibrated on that specific engine for this specific mission. And we have a mission profile and a mission program that's very, very specific. And like you say, it's really knowing your limits, really knowing your upper stage, and saying, look, go this far and no further.
And before we leave this topic and move on to what happens afterwards, talk us through it. So the launch, as it is today, is 9:20 Kourou time, local time. So, and that's currently, I think it's 4 hours behind where we are in Europe at the moment, and they don't have daylight savings time in Kourou, so I think that stays fixed. So early in the morning for everybody in Baltimore. But if it doesn't go on that day, it can go the next day and the next day. There's no sort of super constrained launch window, apart from this bit of not firing at the time when the moon's in the way and hitting that, right? Which would be inconvenient.
I really do love some elements of this kind of mission analysis where you do have to consider things like, for some launches, it's space station and things like this. And effectively, I've understood, for example, with the JWST mission that Ariane 5 will be launching later, that really is like almost a specific day. There really is a very specific day. For James Webb, we don't have a specific day, but it's kind of specific time each day, and that's going to change slightly as the days evolve. So again, it's part of the mission program that is on the launcher, is that if you launch on this day, this is your launch window, or this is your launch time, and then the next day it will be slightly different. And all that is pre-programmed in advance, that we give ourselves some flexibility. If there's any issue with a launcher, with a satellite, or also weather, we don't launch in the middle of a tropical storm. So any issue like that, we're obviously better safe than sorry, more than applies in this case. We wait until the moment is really perfect, and then we'll launch. And so we have ourselves a bit of flexibility on that. Although I think people would like to launch before Christmas.
Yes. We've waited long enough. What the hell? Right?
But that's an Ariane Space tradition. Just so we always do launches just before Christmas. The second Soyuz launch was 18th of December, and they always end up sliding towards closer and closer to Christmas. Everybody getting very, very worried.
Well, indeed, the one I saw in 2019 with Chaos on top, 18th of December. Yeah, exactly.
It's a classic launch date.
Yeah. So it's just like the Americans land everything on the 4th of July, Ariane Space launch things on the 18th of December, so everybody can get home in time for Christmas. Yeah, cool. Alex, let me hand over to you. I mean, I could, we've got lots of other things to talk about, but
there is so much to dig into all of this, and this is the thing that's so fascinating, because it's not just the science, it's the process. It's how we get doors, which is brilliant in a way, hugely dramatic. And just I think that we'll all be watching on the edge of our seat, wherever that seat might happen to be. But Sarah, I mean, so what happens next? Launches happen, that 9 minutes has elapsed, and so on. And then do you sort of like, is it like an Alexa kind of thing? You just sort of flick it on and then see if it works, or what exactly happens next?
Yeah, so the first stages after launch, like the first job, basically, when it's when the telescope is released, is to deploy it. So as we've already heard, the telescope is kind of folded up together, so to fit into the Ariane 5, and that's a kind of mechanically quite a difficult thing, right? So then the first thing it has to do is kind of completely unfold itself. And there's lots and lots of moving parts in there, quite literally. So there is a very finely planned sequence of deployments after launch, which take place in the first, few days to a week or so. Lots of small and big components. So some of it is, the antenna folds out and there's a little momentum flap. But then the really big items are the Sunshield. So we have this huge tennis court sized 5-layer Sunshield, and it's really like sort of like five enormous sheets of aluminium foil or something. If you've ever tried to sort of like tension aluminium foil in your kitchen, It's a bit like that. So that is, has to all be folded out and then very carefully kind of unrolled, the layers separated and tensioned. And it's a very critical part of the observatory. So that is, that's a nail biter for sure. And then the optics of the telescope itself also have to unfold. So we have the secondary mirror is kind of mounted on this kind of like pyramid-shaped strut structure, and that's all folded together. So that whole boom has to kind of fold out slowly and put the secondary mirror in place. And then the primary mirror itself is made up of all these segments, and so it has these sort of two little wing flaps that are folded in to fit into the fairing. So it has these two little wings of mirrors that have to fold out. And those are the really big kind of key components that we'll have to deploy once we launch. And then the next stage after that I think is obviously gradually we are then switching on and testing all the basic functions of the observatory, making sure we can communicate with it and are getting all the information and telemetry back, that we expect. And there is checking and rechecking and constant monitoring. At this point, we are sort of in constant contact with the observatory to constantly be keeping an eye on its health and how things are moving and how things are looking.
So before we go into that stage, let's just step back just briefly back to the initial deployments, because there is that one thing which has to happen shortly after launch, which is the solar array has to deploy, because we've only got batteries on board, and if that doesn't deploy, we have no power. Now, I know that the teams there, you've all been through many simulations of it not working. How do you come out? But it's pretty critical, right? I mean, there are many of these single point failures on this mission, just because of the way it's built. I mean, there's lots of redundancy in many places, but
Yep.
there are lots of things have to go right. And this sort of 2-week period, if I have it right, there's no fixed timeline for many of the things. They will happen when it's time for them to happen. But if it does happen in time, it's New Year's Day, right? New Year's Eve, when the whole telescope will be deployed out. And so that'll be a very interesting glass of champagne I think we'll all be having if that all works. But the reason I wanted to stop you there was because the Sunshield, explain to us why the Sunshield is such a critical part of this observatory. I mean, it's kind of, in a way, it's keeping the telescope in the dark, but it's a little bit more than that. So walk us through why it is that we need a Sunshield.
I've heard it described as it's kind of like the SPF for the telescope. It's kind of it's it's a sunshield, literally. So Webb observes in the infrared, so detects infrared light, and things that are at room temperature, for example, like you and me and everything in your house, kind of emit infrared light constantly. So if you're trying to detect something incredibly faint in space, you have to make sure that there is nothing else around there that is emitting infrared light, because you want to try and observe these incredibly faint infrared signals. So the purpose of the Sunshield really is to block the light and heat from the sun and the earth, to shield the telescope from that, basically. And that would allow the telescope to just cool down to very cold temperatures. The telescope will operate at a temperature of about 40 Kelvin, which is, I wrote this down, minus 225 degrees Celsius roughly. And that's really to make sure that the telescope itself also isn't radiating in the infrared. If the telescope were constantly being heated up by the sun, if it's in the sunlight, it would sort of constantly, its temperature would be fluctuating, and it would have this huge, it would itself be emitting loads of infrared light. And so this Sunshield, its performance is actually like really incredible. If you see how effective it is at blocking the heat from the sun, like the difference in temperature on either side of the Sunshield is incredibly impressive. So that's kind of why it's so important. It's really key to the telescope being able to observe in the infrared. Yeah.
And it comes, people often ask, well, what if one side of the Sunshield deploys, but the other doesn't, for example, does it work half as well? And the answer to that is just no, right? I mean, basically, if it doesn't all deploy and reduce the sunlight by, a factor of 1,000,000 or something, if it only goes 90%, well, it's only reduced it by a factor of 10, and that's just not enough. So it has to fully deploy. And it's not just that it just doesn't work very well, but your instruments don't even turn on, right? I mean, they're not designed to work unless the whole telescope's cold. So there won't be any signals coming from them, from the electronics, yes, but not from the detectors. And talk us through a bit about that. Why is that? I mean, if I have my phone camera works perfectly well at room temperature, why don't these instruments work at room temperature, the ones we have on JWST?
Yeah, well, they were very much designed to work at these very cold temperatures. So the MIRI instrument, in fact, gets cooled even colder because it observes longer wavelength light and is actually even more sensitive to these kinds of faint infrared background sources. So we do actually have a cryostat on board that will cool MIRI further down, but that's of course also optimized to operate in a certain kind of thermal environment as well. So if the whole observatory is way too warm, then it's going to be really difficult for that to function properly as well.
Yeah. So these detectors, because they're detecting very low energy photons, when it's warm, they just give off electrons, and the electrons just fill the detectors up, and not with anything useful, just background, right? I mean,
exactly.
Dark current.
Yeah.
So MIRI has this additional cooling system, and that's all a bit weird too, right? Because that's kind of attached to the warm side of the telescope, and you don't want any heat to be transferred along that line. So it's got this very weird thing, the slinky. Maybe you can talk a little bit about that, because that's sort of one of the weirdest things on the telescope to me, because I mean, it's to do with the way the telescope separates from the spacecraft. That's one big thing that has to happen when we get into space as well.
Yeah, so the cryo cooler that there is on board is kind of a new kind of technology as well, that was developed at JPL in California. And so yeah, it is actually kind of, rather than sort of traditionally you have a big vat of a cryostat, and sits right, that your instrument is actually like inside of or something. In this case, it's actually kind of very physically kind of spread out. And so the main kind of part of the cooler is not right where MIRI is. It's actually physically kind of separated from it. And then we have these kinds of thermal straps that help kind of pull all the heat that cool the instrument basically. It's a completely closed system, so we also don't kind of run out of coolant. It's actually a question I get asked a lot, like what's the lifetime of MIRI, given that it needs coolant?
I was going to ask that one exactly, because the Herschel lifetime was defined by the helium it had on board.
Yeah, so we have a complete kind of closed cycle, closed system. So that is not the thing that limits the lifetime of the mission. That was, as Mark said before, it's actually the propellant on board. Yep. So MIRI gets cooled down to about 7 Kelvin. So a few tens of degrees Kelvin lower still than the rest of the observatory. It's also one of the reasons that MIRI will, because MIRI has to wait until it has reached that very low temperature after launch. So it's actually one of the last ones to get switched on and start to get commissioned in that whole commissioning phase as well, because we have to wait until we're cold.
So let's talk about that briefly, because there's this kind of expectation. You launch a new telescope, particularly one that's so long awaited, and everybody's sort of anxious to see the images, and there won't be any for almost 6 months, because there's so much to do. It's to turn things on and commission them, but also Nurcam has this really critical role to play, because we've got these 18 mirror segments. So maybe you could talk a little bit about that. What does that mean? I mean, we've got 18 individual mirrors. We've got to line them up somehow.
Yeah, that's exactly what needs to happen. And once the telescope is deployed and we know we can talk to it and everything, that's a kind of the next big job after launch, is that we need to line up the mirror segments to make sure, because basically you have all these individual segments, but ideally you want them to act like it's one continuous, incredibly smooth mirror surface. And so each of the segments can be controlled in different degrees of freedom to achieve that. So there's this whole sequence of events where we look at stars, just simple point sources, with each of the kind of mirrors sort of individually, and then really make sure that we line them up perfectly to get like this one perfect sharp image, basically with all the segments working together as one. And the tolerances on that alignment are incredibly tight. I don't know what the actual number is, but it's probably sort of, nanometer scale of that kind of order. And so for that, we use the Nurcam instrument. So Nurcam is the kind of workhorse imaging camera on board the observatory. And it's a beast, basically. It has 10 detectors on board. And it's actually like fully redundant. So it has sort of 2 identical copies of itself. And that is really because it is so critical for the mirror alignment. Because, if we can't align the mirror properly, then, all the science will be affected. And so really, to make sure that we have a working Nurcam instrument, we basically have 2 copies of it on board. And if everything goes well, then we have, basically both of these sides that we can use for science. But it's also really that each of them can operate independently if they need to.
Mm. And then we shouldn't forget the Canadian contribution as well, which is kind of critical in this because it's a scientific instrument, this slitless spectrograph called NIRISS, where you're going to get little spectra of galaxies and stars without actually having to put them down slits. But then there's the fine guidance sensor, which is, again, people don't quite understand that, how do you accurately point a telescope and keep it fixed to a very high precision? So talk us a little bit through how that fine guidance sensor works.
Yeah, so as you said, this is one of the Canadian contributions to the observatory that is the fine guidance sensor, and that's basically it kind of operates all the time when we're observing a target with one of the science instruments, and just make sure that we keep the target pointed very accurate, the telescope pointed at the target very accurately. It's basically, a sort of a type of imaging camera, but that is, whose detectors are completely kind of designed to track the position of a target incredibly precisely and ensure that it stays sort of within one of its pixels. So again, very critical part of the process of observing with Webb, and all space telescopes.
I mean, it reminded me, because you said at the beginning that you worked on adaptive optics on the ground. I mean, there's this weird fine steering mirror in James Webb, which Hubble doesn't have, for example. Hubble just sort of tracks with fixed optics, but we even have a wobbly mirror inside James Webb to sort of take the jitter out, because it's this stupidly flexible telescope, right? It's not exactly a rigid object, James Webb. It's not kind of, I won't say brick shit house. Well, I just did, but it's it's kind of not solid, right? I mean, it's just waving around because to do science, we actually have to move the telescope around and point at different places, and the Sunshield will adapt, and everything has to move. And this fine steering mirror helps us out, right? I can't remember do you remember the speed? I don't. I mean, it's not a rhetorical question. How rapidly the FSM works? It's quite quickly. I think it's not like.
Yeah, I don't actually know what the speed at which it operates now. I kind of know roughly its range in, kind of on sky. But because often if you need to make small movements or dither patterns or things like that in observations, it's kind of like you kind of playing off the telescope and the fine steering mirror together to optimize those movements. But I actually don't know how long, how fast it moves. But it,
So. It's amazing how quickly an hour can elapse, especially when we're having a great time talking about all these subjects. And we have people joining from all over the world, Canada, Berlin, even the BBC, popping by to kind of say hello, which is fantastic. And so I want to kind of welcome everybody to the show once again. And I wondered if we could just ask a couple of questions, that have come in from the audience as we draw toward a close, because, I mean, I think suffice it to say, this is not just a momentous occasion for science, it's a huge milestone for all of humanity. I mean, just what an astonishing achievement it is to get this far. The ambition and the potential of the James Webb Space Telescope to change the way that we see the world, the universe, and our place in it just kind of takes my breath away. And some really good questions have come up that we really should try and find some time for. So, what's it going to see that other instruments haven't been able to see? This is coming from Martin. And well, what's going to happen to things like the Hubble? I guess you just sort of put them up on the shelf then, or is there still a life to be lived for things like Hubble, which I guess comparatively speaking, I guess these are aged instruments, but do they have a life left?
Well, let Sarah take the one of what we're going to see with Webb. Because we're going to see lots of things, and Sarah, you should talk about some of the things you're particularly interested in.
Yeah, it's so Webb was not designed for one particular type of observation. And as I mentioned before, like we have this instrument suite and with 4 instruments, and each of them have like lots of different types of cameras and spectrometers on board. So it's really designed to be able to address the widest possible range of questions in astrophysics. And we already have our entire first year of science kind of, the programs have been selected. So we already know the targets that we're going to be looking at, and that's all publicly available. By the way, you can all look that up on the web pages, and it's just fantastic to see what people are planning to do with the observatory. So it's like everything from objects in our own solar system to exoplanets around other stars in the galaxy. That's going to be a huge area of research for Webb. And really, Webb has a lot of like really unique capabilities that we've just not had before in a kind of space environment that is incredibly stable and cold. So in terms of like characterizing atmospheres of planets around other stars, I think that's an area where we're going to, learn a lot of very new things in the next few years. But then all the way to like the very first galaxies in the universe, really. And everything in between. So even, at the sort of low and intermediate redshifts, we're going to be able to observe galaxies over, even the tiniest galaxies, at the kind of distances where maybe right now we can only see the really big whoppers. We'll be able to see the really tiny ones, the really young ones, or we'll be able to really see how stars are forming inside them. Supernovae out to vast distances. So it's hugely exciting. Yeah, we're gonna and I'm actually involved in programs both on the exoplanet side and also the very early universe type of galaxies. So I'm going to have a lot of fun with these when these data start coming in.
Just to pick up the thing you said there, of course, when it was originally first conceived in the late 80s and then through the 90s, exoplanets didn't even exist. In the sense that we didn't know of any. And that's a remarkable testament to this observatory, is that it is a general purpose tool. And there were some modifications made for exoplanets, but not many. And so the fact that we can do that is a testament to the breadth of ambition that the observatory had. And then just to pick up on that other area, are these very first galaxies, just to go through that briefly, right? Hubble can see to a certain distance in the universe, which corresponds to a certain look-back time, because, of course, light travels at the speed of light. We can see back to galaxies which formed in the relatively early universe, but not in the very first ones, because the universe has expanded and all of that light has been redshifted into the near and even into the mid-infrared, right? Yeah. Some parts of it. And so we need a big cold infrared telescope to see the very first galaxies that ever formed. So I think that's kind of the headline one that's always been there. JWST, the first light machine. But as you say, I'm going to be looking at stars and planets and forming in our own Milky Way today. Some people will be looking at the thing behind you, right? We can look at Mars, we can look at Jupiter, we can look at Saturn. Which is tricky because they're moving relative to the stars, and we have to be able to slew the telescope around. It's all interestingly complicated. I see we've lost Alex, and I hope that doesn't mean we've lost the live stream, but we just keep talking anyway because he's in charge.
I had an engineer's question exactly. So understand that there's a process with satellite is that the telescope you've defined, it's been defined, and so we have people have an idea for the instruments, but you say to the scientific community, we're launching this. What do you want to do with it? Please give us your ideas. And then it's also up to individual scientists to say, oh, that instrument, I could do this with that instrument. So in fact, when you build a satellite, you don't know, you have an idea what it can do, but you don't have a full idea. And you really let the entire global scientific community come up with their ideas for use.
Yeah. Before Sarah picks that up, the critical thing is exactly that. Global. Anybody can apply for it, even though it's built by North Americans and Europeans. Anybody in the world can apply for it. It's open in that sense. And it's highly competitive, of course. So it's not easy to get the time. But yeah, I mean, there were certain tentpole things that we said we want to be able to do this. So we need that diameter, we need that temperature, we need this kind of instrument. But that just sets out the kind of the panoply of possibilities, everything else in between. And Sarah, you just, because you've been part of that process, how do we pick, right?
Yeah, it's actually really fun because as Mark said, the scientists, the astronomers are involved in the design process as well. There is a sort of constant iteration between the science and the engineering while you're kind of refining the design of the telescope. But then sort of like opening that up to the entire community is something, we've been really doing. That's kind of a lot of what we've been doing the last 2 or 3 years. And it is amazing because people come to you and they have these ideas that you just had we really hadn't sort of foreseen, or they have this whole new things like one very interesting thing that the questions that I fielded is, people who do X-ray astronomy. And in X-ray astronomy, people really have they've almost have the exact arrival time at the detector of each photon. And they really, so they have sort of millisecond accuracy on, when things occur, when photons get received. And then they turn up at Webb and go so we want to do that with Webb. What's this kind of timing accuracy down to the milliseconds of when an image is recorded. And for an observatory operating at L2, in the infrared, where you're not receiving 10 photons, you're receiving an awful lot more than that. Then, and with lots of different clocks on board as well, that each kind of do their own thing a little bit. You're who knows the answer to this question? So you get these really fascinating then conversations, and that's how you learn, and we kind of learn how to actually operate the whole spacecraft for a particular science. So it's actually been a really fun process.
I think if I'm right, we had an oversubscription on the first round of roughly 4 or 5 to 1, and that's somewhat less than Hubble has got to, where it's around 10 to 1. So 10 proposals for each successful one. But I think it's a lot of us have been reflecting on why is that? Why is it sort of not under demanded, but less demanded? I think it's because it's so capable. There's so many modes, so many ways of using it, that at some level people want to see some data so that they can start figuring out how to use it. And I think that's one of the things, before we move on to the next question, we will be releasing data completely freely, available to everybody to look at as soon as we get it, so to speak, these earlier release observations, which will then say, this is what it looks like, go and use it, figure out what you want to do for the next round.
Well,
exactly. Yep.
It's something that's often overlooked. And Mark, I'm sorry to put you on the spot here, but we are getting questions from the audience, and we always do our best to fit them in there as well. I mean, at the very top of the program, we actually talked about your own journey to Kourou, and Jonathan Amos is on tonight.
Of course he is.
And he was actually he had a question of a different sort, but I think it's an important one. What did you feel the first time you walked into that room? The first time that you saw it in person?
As Jonathan knows full well, that's an incredibly meta question, because the moment I walked into the room, he had a microphone under my face recording what I felt. So for him to ask that when he's got the only recording in the world of what I actually said, but he's right. I mean, it was a sort of a strange moment, I think. I mean, effectively the observatory is currently standing vertically in one of the big clean rooms there in French Guiana, and your access as a visitor, not going in with bunny suits and so on, is to walk along a very mundane corridor through a very mundane office building and then walk into a room, and as you walk up to the window, suddenly this thing is just standing in front of you, and it's really close. I mean, it's not like kind of off in the distance. So firstly, it was an astonishing privilege, I think, to be able to see it, because those who go to the launch won't be able to see that. It'll be in the fairing. It'll be too late for that. And in some ways, I think, this all sounds strange, it was a little bit difficult to know how to react, because I've been involved with it for so very long. And in different ways. I mean, I was part of the proposing team in ESA in the early days, but my involvement since then, or through the phases of being on the science working groups, as the engineers have taken over, and people like Sarah who've been working day and night to build the operations and the people building the launcher, my role is certainly much more distant. So it was a sort of an odd moment of, how do I react? Now it's finally there after more than 2 decades of thinking about it and seeing pieces. I mean, Jonathan said, how do you feel? And I said, hopefully this is what I said, I said, you really expect me to find words at this point? I mean, I really, because he had primed me, he said, I want to record you doing this. I want your reactions. I said, I'm not going to do a meltdown. I'm not going to blub or anything. That's just, I'm too British for that. And I didn't, but I think there was emotion there, and he caught that, and it was a very, and you, so of course, Sarah, you've seen it many times in the testing. Did you find yourself kind of looking over your shoulder at some points and think, it's not just the thing I'm working on, it's something more than that? It's kind of has a presence, right? It's such a big thing.
Yeah. I mean, yeah, absolutely. It is quite weird because I'm so familiar with what it looks like, because I deal with sort of images and things like every single day as well. But at the same time, seeing it in person, I mean, it is always the scale of it that is always, I'm always taken aback, if I haven't seen it in a while. Because I mean, I have seen it, but not like on a daily basis. It's even in the test campaigns, often it's through like a tiny window or something. So, and the size of it, even though I know what it looks like, I'm incredibly familiar with all the bits and pieces, but the actual scale of it every time, it's just like, wow, it's a really big thing. And I've definitely found myself like now going towards launch, like getting kind of more emotional about it and kind of all those extra things that it means, definitely coming up more.
Yeah. I mean, weirdly, I was filmed I was doing interviews for various media, and I'm kind of in that room for 5 hours, constantly talking about it, but occasionally sort of looking over my shoulder at it. And at some point, it almost became sort of in a weird way, I don't know, almost deconstructed itself. You know how it is, for me at least, occasionally if you're reading a story about badgers, by the time you get to the end of the thing, the word badger doesn't mean anything when you read it anymore. It's kind of become, what is that BADGER? I can't see that word. It was a bit like that with the telescope. It was just kind of there so much. I don't know, it seems like a really weird way of saying, was it actually real? Is it actually there? After all these years, it became quite an experience. And there were no drugs involved, I can assure you, apart from caffeine. That was the only one. But
for me, it's all
French Guiana.
For me, it's always like the watching all the engineers and technicians in their bunny suits in the clean room. I just watch it and just like, your job is incredible.
Yeah.
You spend all day in the room with this phenomenal, piece of engineering. And there's so many amazing pictures of them like hanging off the diving boards and just like doing stuff. And it's just like the expertise and the diligence is quite amazing.
Yeah, I think that's the thing which we can never say it too often, right? This has been 10,000 people, plus or minus, working for 2 decades. People often say, why is it so expensive? Well, just do the maths, right? I mean, that number of people working for that long to build something that complicated, nobody's spent the money on a yacht or anything. It's built that machine through people's fingers and brains and long nights. It's true of everything we do in space, right? It's people. It's all about people. And I just don't think, you've got a couple of people here involved in the project. We could do an uplink for the next 20 years, pulling in people one after one, and they'd all have amazing stories on the thing they did, because there's nobody on the project from bottom to top that is kind of just, dialing it in, right? Everybody has a story to tell about the thing they did that made this thing possible. I know that sounds all very, grandiose, but it's really true. You can talk to anybody on this project and get a story. I mean, even Sarah and her surviving the hurricane in Houston, right? I mean, all the people were down for that, where the whole of Houston was flooded, and they were testing this amazing space telescope at the same time.
Yeah, there was like plastic sheeting over the consoles to make sure that the water that was coming through the ceiling stayed off us.
That's not my office. That's my shed, actually. That's why I always have this virtual background. Exactly the same. Yeah.
Sounds like French Guiana as well. Yeah. Thanks.
Indeed. Well,
Yeah.
speaking of stories, I mean, Mark, you're so right. And I mean, these have been two incredibly important stories to share. And so, Kate and Sarah, what an absolute pleasure it's been to be joined by you. And it really feels like we're just at the beginning of this particular story. I mean, there's so much to talk about what's taken us up to this point. But the thought that we're just at the very start of this next chapter is so exciting, And so I think, like so many people around the world, we'll all be watching, and for fear of being anti-scientific, maybe crossing a finger or two, and just I guess waiting for that first information to come back. But first, a lot else has to happen. So I'm sure I speak for everyone who's watching this evening, and a lot of people around the world when I just kind of salute what you do, because it is absolutely inspirational, And I wish we had more time, but we will have to have you back, because we would love to follow up and find out what happens next, and indeed what happens next. So yeah, exciting times, and thank you so much for joining.
Yeah, thank you both very much. I mean, hopefully, we'll get to see each other, which hasn't been true for a very long time. I mean, and it's always good to meet in person, and hopefully we can get you to some of our live events when we do it. Fingers crossed that although I won't be at the launch, I may well be in a room somewhere near to you at the time, Sarah, in Baltimore on December the 18th.
I will probably be in Kourou, actually.
Oh, you will? Okay.
Everybody's moving. I might go to the Netherlands for a launch event, so you go to Baltimore, and then Sarah.
Who knows?
Sarah goes to French Guiana.
It's all up in the air at the moment, but a lot of people will be watching from wherever they are.
Yeah.
But there's one tradition we cannot miss. I mean, Kate, you know it, and that we would like to sign off just because we can. So we like to do a little double hand salute. This is the Vulcan salute for space, and the horns for rocks. Space rocks. Perfectly done. All right.
Sorry, we're losing some fingers.
You've separated. Yes, right. That's right. That middle bit there. Thanks very much, both of you.
Thank you.
Thank you. Lovely
so much.
to talk to you.
Thank you so much for your time.
Bye-bye. Thanks.
Bye.
Be well. Fantastic. Well then, Mark, I've got a little confession to make. What an absolutely thrilling chat. It never ceases to blow my mind, just what we're talking about. But yeah, so Jonathan, our friend from the BBC who's joined Space Rocks Uplink, and of course, who you know very well, says, I mean, yeah, you had quite an emotional response, and I think that it's completely warranted. I mean, I can't quite imagine what it must feel like being in the room with a thing that I guess you've been kind of thinking about for 23 years. What an experience.
Well, as Jonathan, quite emotional in Jonathan's terms is my stiff upper lip slightly quivering at one side, but yeah, no, he's right. I mean, and we spent a very good couple of days down there with all of the teams, the NASA team who were there putting it together, making sure everything's ready for launch, the Ariane Space team, the European Space Agency team, and the Canadian Space Agency guys, everybody there doing everything necessary to get us to that December 18th, 9:20 in the morning in French Guiana. And everybody, again, has their journey. They have their thread through it. And there have been times when I've been deeply involved on a daily basis, and other times when it's, there have been weeks and months where other people have been handling everything. So it's always difficult when you do media on this, is also to over-represent your own role. That's the temptation, right? You become a focus. And I think it always sounds a little bit, pretentious, but it's everybody else. It's a massive team effort, and it's an international collaboration as well. Let's keep that in mind. I think everybody should keep in mind on the day. Obviously, it's being launched on a European rocket, but half of the instruments on board are European. There's a Canadian instrument on board. There's a US-led instrument on board. I mean, it would not have happened without us all getting together around the end of the 90s and saying, this is what we want to do. What can you bring to the table? What can I bring? And here we are. I mean, it's been a long journey, and there have been troubles along the way, definitely. Problems which had to be solved, which were not thought of originally. But if we weren't doing difficult things, if we weren't faced with these challenges, we wouldn't be doing the most amazing science at the end of it as well. So, yeah, look, it's too easy to say I'm very proud of everything, because, of course, if it doesn't work, it doesn't work. But I think we're pretty confident at this point that we've done everything we possibly can to get it ready for launch and operations starting next year.
Indeed. And an exciting point in time, the history of human discovery, and also just from a visceral level, Mark, it's going to be quite the thing to watch. Just only takes a little information.
Yeah, when that day comes, I mean, any notion of a stiff upper lip will disappear, I can assure you.
I'm sure I'll be joining you. I'll be right there with you. As ever, an absolute pleasure, Mark. And thanks so much to everyone who's joined us for the 60th episode of Space Rocks Uplink. Now, there's a number.
There it is. Thanks very much, everybody. And hopefully we'll be back in a couple of weeks' time.
We'll talk to you soon.